So greetings, scholars and young professionals in high-performance computing, computational science, and engineering. I'm very grateful to Paul for bringing me here today, mainly because I want to hear all the other talks today. But I'm also happy to be able to seed the transition from the programming models to the algorithms by means of a talk called Algorithmic Adaptations to Extreme Scale. If you downloaded any previous version from the website before this morning, you may want to refresh with version 3 because I've made some permutations. There are no accompanying hands-on exercises as a departure from your previous lecturers. I will, however, assign several thesis topics. And I will illustrate the assignments with several actual theses being pursued in the ECRC at KAUST, which has twin pillars, one of them much like the SIDAC program from which the rest of today's talks come, namely creating algorithms that scale to contemporary architectures and assist high-performance users in need of multiple scales and so forth onto those systems. And the second thrust has to do with preparing for the exascale as guided by the projections for architectures and system software that have come to us from the G8's International Exascale Software Project. So you're encouraged to join the fun of pursuit of the exascale. There's much room at the frontier. Everything I'll say today is speculative, but the results may be required sooner than we think. And every step that we make towards reducing synchronization, reducing communication, enhancing SIMD-like multi-thread concurrency, all these advances will be immediately applicable at the petascale as well. And that's a theme that we've seen in the last couple of days. So we were encouraged by Paul to make tie-ins to one another's talks, and I haven't, of course, heard the other talks, but I predict that several of today's talks will pick up on things that I will pass over all too briefly with the excuse that more thorough descriptions are coming. So if I've read the program correctly, we're likely to see a lot on communication reduction and really knowing what's achievable and quantifying the trade-offs between communication and extra flops or extra memory, hierarchical exploitation of low rank, multi-level methods, Newton methods, and then a panel in planning for extreme scale where you'll hear the actual developers of the world's best open source PDE and solver and meshing and partitioning libraries and so forth discuss their challenges. And then next Saturday, I believe, Jack Dongera will be here with a talk that also ties in today. I might preview a slide or two from his directed acyclic graph-oriented revamping of linear algebra to increase concurrency and reduce synchronization. So your generation is unfortunately at a pivot point. Well, actually, that's very fortunate from the point of view of finding good thesis topics. From about 25 years of bulk synchronous programming to a generation that's much more energy aware and has to be conscious of moving data and of, with billion threads, you can't synchronize very often, very effectively. Hardware isn't that reliable anymore, even if you can perfectly load balance. And these will disrupt a lot of the very satisfactory software tools that we sell to users today. The concept of BSP you've heard ever since, I think, the first day. It goes back to a 1990 paper. At least the words do. The concept was somewhat earlier and is, of course, the basis of the 1992 MPI revolution in scientific computing. I encourage you to read not just the abstract, but the entire paper for its historical importance. BSP has a very impressive legacy brought to the present day. These are a few decades of the Gordon Bell Peak Performance Prize that extrapolate quite well in terms of clean ratios, 1,000-fold every 10 years, some of that coming from the microprocessors, but a lot more of it coming from the concurrency. And it's not just the flops if cost are no object, but the cost per delivered gigaflops in terms of the installed price of the machine is on almost as impressive a curve of about 1,000-fold reduction every 10 years. And I think I took this picture from the European multigrid community because I'm sure you're going to hear and see some impressive ones from Rob later today. But basically, it's been an extremely successful foundation for weak scaling, for making problems that can fill up a machine as big as we can get with actually meaningful flops in terms of resolving multi-scale phenomena. And the bottom curve here is the cost of solving an elliptic problem from 36,000 degrees of freedom on one processor to 8 billion degrees of freedom, a quarter of a million size larger on a quarter of a million processors with almost constant execution time. That's very strong weak scaling along with the assembly and, of course, the overall. So the problem is that extrapolating these exponentials from the Gordon Bell Prize will eventually hit some physical limit, and scientific computing is at that crossroads now. From giga to tera to peta, as you heard the Cray people say yesterday. It's been just every 10 years, but I don't think it will be 2018. But we've been able to use the same BSP programming model, the same assumptions about who's responsible for what part of the computation. And although there's been a lot of algorithmic innovation, the same basic classes of domain decomposed or data decomposed algorithms. But EXA is qualitatively different. It looks more difficult. We once said that about message passing. Turned out that pretty soon everybody had adjusted, so we can have some confidence. But I believe that no matter who you are, a core numerical analyst or a user, you will have to confront in even your part of the code the port to these more disruptive architectures. It's not a distraction, I would hope to convince, but it's an intellectual stimulus. And I think the journey will be as fun as the science that will be at the other end. A couple of times today I will refer to hierarchical algorithms derived from the fast multipole method, and this is a paper that just appeared in Jack Dongarra's brand new journal, Supercomputing Frontiers and Innovation, or you can turn from some of the details that I'll go over extremely quickly. The main challenge going forward for bulk synchronous processing is that almost all of the good algorithms are addicted to very regular synchronization, whether it's inner products to do projections, norms to find magnitudes, refreshing a global residual. This has been a very mathematically good way to construct algorithms, but it tends to hurt efficiency beyond about 100,000 processors, and it can even be fragile for smaller concurrency if you have any kind of adaptivity that has to be micro-balanced or hardware performance variation. And concurrency is heading to another factor of 1,000. So this is, a sign that we should try to reduce synchronizations. There are plenty of ideas that, to adapt our favorite solvers or to substitute them with modified versions that reduce synchrony either in frequency or in span. So, if we synchronize often but within smaller subgroups most of the time, that's another possibility. Greater arithmetic intensity, boosting the ratio of flops to the more expensive memory transfers. Greater SIMD style for the kind of CUDA expressiveness you've heard about, shared memory concurrency, and increasingly built-in resilience. That will be more and more the province of the code designer because it will be energy efficient and shorter time to solution to not have the system software try to do everything with voting on errors or checkpointing or whatever. So programming models and runtimes will be stretched to accommodate these architectural disruptions, and everything should be on the table for trades, even the math models that before you discretize them. And this is, of course, the buzzword co-design that is occupying a lot of, and worthily so, a lot of attention today. Instead of the classic separation of concerns, looking over the interfaces to try to find synergies. So I have 5 slides of bad news, good news. One will explicitly have to control more of the data motion. We already have been doing that for horizontal data motion in the BSP world, but now we'll do more of it in vertical data motion, cache transfers, and so forth. We've already gotten used to that with rolling things in and out of GPUs and taking over some of the layouts decisions that were made for us. The optimal algorithms that we know and love may lead to poorly proportioned computations for exascale hardware resource balances, because they've been designed to squeeze out flops, and that's no longer the chief game. But this may be a good incentive to lure scientific and engineering users into more arithmetically intensive formulations than mainly PDEs. Integral equations being a good example if you have something that's linear. Bad news and good news on reliability. We may come to regard hardware reliable computations as too costly, and algorithmic-based fault tolerance will be cheaper than having the OS or further down do everything. And I believe that developers will ultimately partition their programs and their data into 2 sets. One part that has to be executed and stored and retrieved reliably, like today's computing, and one part that can be done faster with less reliability and less energy cost, knowing that errors either can be detected or their effects rigorously bounded. For 50 years, we've been forgiving the hardware for floating point rounding through the numerical analysis of stability. And so we commit quadrillions of errors per second for weeks, and we trust the answer. And maybe there are other ways where errors from the hardware can be brought into the programmer side. And there are plenty of examples already, and you'll hear, I think, of some in Jack's talk in a week. And this was, of course, anticipated by von Neumann, because digital hardware wasn't always so reliable. And so we may go back to some very early roots of the subject. We will maybe not use default high precision on nodal bases on dense meshes. That's an incredible waste of bytes for representing functions that may be continuous. And it's a lot of, when you have big size, you have big bandwidth. Hierarchical bases are much cheaper, communicating the deltas, the last few digits that change over a course of many iterations instead of restoring the entire state variable, may be more efficient, like iterative correction in linear algebra. And maybe we'll even have some of those smarts go into the hardware so that we can still program like we did, but the hardware will say, oh, you're sending that message to that guy again. Almost all the bits are the same. Here are the ones that need to be updated. So that's another co-design issue. And equidistributing errors to minimize resource use will lead to innovative new topics in numerical analysis. Finally, fully deterministic algorithms may be regarded as too synchronization vulnerable. Instead of waiting for data, we may predict it. After all, the functions are smooth, the operators are often low rank, the high frequency components often diffuse quickly, et cetera, et cetera. You get the idea of how the model comes into helping the algorithm be more efficient with less reliable hardware. And in some sense, machine learning is growing. We know how to make scientific predictions when we don't even have a model, as we heard last night from Valerio. And maybe in a much easier way, we can make some scientific predictions that get us out of some of the more rigorous requirements of predictive computing as well. So, yeah.
So this includes randomized algorithms?
That's a good point. I haven't. I should insert that. There's one bullet from last year's August exascale math meeting later. But thank you very much. Yeah. Okay, so some caveats. So I've now maybe created high expectations that I'm going to tell you something about how to solve these problems, so I can't. But I think I can make a few points of light here and there with the expectation that a full picture will emerge. And just as another caveat, you might actually be able to ignore this talk for 5 years or so, but not for your careers. So I might be able to ignore it. So if I'm making the leap as an old man, I encourage you to do the same, because it should be fun. I referred earlier to the G8's exascale roadmap, which was published a few years ago. You heard Pete Beckman, who was one of the co-leads on that, to kick off this workshop. It's, things go out of date quickly in terms of, hardware predictions and so forth, but the general thrust and directions that are documented in this long document are worth catching up on. What I have learned from IESP meetings is that in the pursuit of low energy computing, we will become less reliable. Voltage differences between 0 and 1 will be reduced to admit more noise. Circuit elements will be subject to more noise, so there'll be more errors to be caught and corrected by somebody. Power may be cycled on or off, or clocks slowed or speeded to prevent things from melting, to adapt to machine learning on the use of compute resources by the machine itself, and so forth. This will make per node performance less reliable, and it introduces this impediment to global synchronization. I believe that expanding the number of nodes beyond the current million in a weak scaling sense would not be a difficult challenge from the point of view of algorithms like multigrid and fast multipole and so forth. We can weak scale fairly indefinitely because of good surface to volume ratios and communication and computation ratios if there's a fixed large problem per node. But of course that raises the expense of the computer in a linear way as well. And this would only be true if the nodes remain performance reliable. But the real challenge for all of us is the strong scaling within a node in shared memory. And you can actually do that without waiting for an exascale computer, because just working on the nodes and then multiplying them by 1,000,000 will probably be the first exascale computer. So the philosophy that I would like to propose is that algorithms are, where the buck stops between the demanding applications and the increasingly austere hardware that we're going to get, that we're even asking for energy efficiency. And so this is a full employment program for computer scientists and computational scientists. And just recently, in preparation for Corey at Berkeley, I noticed they're advertising 8 new postdocs to help migrate users towards that system. Oak Ridge is adding 3. I just heard a couple of weeks ago at CSGF. IBM just announced this week 10 new postdoc positions at Watson to help them migrate to their Power NVIDIA system. And so there's going to be a lot of, like I said, full employment along this line. Those are just examples of recent. Motivation for algorithmic attention is because of the campaign of the multis, right? Multi-scale, multi-physics problems in all dimensions, using multiple models, multiple levels of refinement, exploiting polyalgorithms as hardware and problem size barrier shift and expose better algorithms in different regimes, or as the physics changes and does the same thing, and in adaptively multiple precisions, maybe in a multi-protocol like MPI plus CUDA or whatever, programming style, on multi-core, massively multi-processor systems, all requiring multidisciplinary teams. This is the driver from the DOE sponsor's side that motivates the attention to algorithms. So the basic question is, how can algorithms help, given all these stresses that are sort of disruptive? And I think I can be very quick here to just remind you that all the projections from the DARPA semiconductor roadmap show that there'll be a reverse in the 25-year-old culture that we're in, that flops are expensive and memory is flat. Moving stuff around in memory or across network will be much more expensive than actually doing the flops, and this will change a lot of the paradigms. So here's an example for the 2019 Intel whatever. This double precision floating point multiply add, retrieving 3 arguments and storing 1, will only take 11 picojoules to execute, but about an order of magnitude more to send those bits across the die. Today, it's already a great ratio that's quite similar. All these costs will hopefully go down, but it's 2 orders of magnitude versus transmitting a word across the system to operating on it in the destination core. And remember that a pico of anything, pico looks small, but a pico of anything done exa is a mega. So if you have a picojoule, an exaflop, you got a megawatt. And a megawatt adds up. I mean, a megawatt year is $1 million, and you and I as sort of OECD citizens use about 1.4 kilowatts continuously. So a 100 megawatt computer made, just for the flops, energy estimate for this current system, an exascale computer made out of these components would eat up the power otherwise available to 71,000 people. So we're obviously heading towards a power austere world. And what changed is that in the old days you could scale by increasing the doping and reducing the line widths, and the power density per square centimeter would stay the same as the flops went up, proportional to k squared. But that was true for the semiconductor, but it wasn't true for the copper vias and everything, which as they get smaller, increase the resistivity. And this was known 4 decades ago, that we were eventually going to hit this point. We maybe didn't know when we would hit it. What will the first general purpose exaflops machines look like? Many exciting hardware designs out there, carbon nanotubes, DNA, quantum computing and so forth, but not in the next decade. We'll be still using some kind of CMOS silicon etched logic, and we'll probably still be using some combination of distributed memory message passing plus strong scaling within a node, whatever that is. Some themes: clock rates cease to increase because power is quadratic to cubic in the frequency. Memory storage also, memory storage improves, but below the concurrency growth of the processors. Transmission capacity improves, but below the arithmetic capacity. Mean time to failure shortens, and billions of your favorite, G8 currency of scientific software hangs in the balance. What's that software? Well, today you're going to hear mostly about software at the top of this model related stack that Lori will introduce in a couple of hours related to setting up your problem and doing, the actual scientific deliverables, going from the continuous to the discrete world. Then there's, of course, all the development-related software, and then the production-related software. And vendors, supply relatively little of this with a new system. It's mainly made by graduate students and then hardened by postdocs at DOE labs, and of course used and debugged by the world. And so that cycle has to be begun again for a lot of these concepts. So that's the area where I personally choose to work. So how are most of scalable iterative methods based on domain decomposition implemented? All the data structures are distributed. You can't have any centralized that have a billion objects in them. Each individual processor works on a subdomain of the original, running the same program on different data, exchanges a boundary amount of information, which is subdominant compared to the volume computation, and both the communication and the computation are fully parallelized, and their ratio is supposed to remain constant in weak scaling. You heard a nice counterpoint to this last night from Sanjay Kali about not using the network only a tiny fraction of the time on synchronization points, but trying to smooth out the use of the network. That's a good philosophy. But the majority of the codes that you hear about today are in the bulk synchronous mode. And so you have this surface to volume beneficial effect that you can do a lot of computing for a relatively small amount of communicating, and both can be balanced. So just to recap the agenda going forward, we need greater arithmetic intensity because the energy ratio has shifted between doing flops and moving bytes, including assured accuracy with adaptively less floating point precision where possible, because if you can have your precision, you've doubled your memory and your memory bandwidth. Reduced synchronization and communication, either less frequent or less global. Greater SIMD-style thread concurrency for the natural way to program accelerators, greater algorithmic resilience to faults. Quantification of trades between limiting resources, plus actually using this stuff to do, why the government will pay for exascale computers. Parameter inversion, data assimilation, uncertainty quantification, optimization, engineering design, decision support. Those loops around the forward problem that we spent the last 25 years making scale well to peta. So now I'll go into a phase of the talk where I will illustrate some thesis topics, if you will. Little points of light, no comprehensive replacement of one library by another, but examples of how you can execute some of these algorithmic agendas. So I'll talk about fast multipole and then an algebraic generalization, nonlinear preconditioning for Newton, rewriting of sort of the blahs in a directed acyclic graph way, implementing them on GPUs, and sort of a new way to think about programming large-scale PDE codes. And many of these themes, at least the algorithms behind them, will be fleshed in throughout the day. So the first one, which is the longest example, perhaps it's very familiar. It was the topic of the von Neumann Award this year at SIAM earlier this month with Leslie Greengard, is the emergence of fast multipole as a sort of do-all method in not just Poisson, but any operator with a Green's function which has sufficient decay. And one of the motivations for fast multipole is its tremendous arithmetic intensity. So on the bottom axis here, you see flops per byte. So why is SPMV a quarter? Because if you have X cached and Y cached for updates in Y equals AX, then each double precision floating point multiple add costs you an element of A, which generally can't be cached because A is big. So you have 8 bytes, 2 flops, so a quarter. And at that stage, you're not using your flops. You're limited by the memory bandwidth. And this is the famous roofline plot from Sam Williams at Berkeley. And you want to work in this regime where you're using the processors that you've paid for. And these curves each go to a different contemporary chip. And these lines represent different kernels. So there's the 3D FFT. And under certain assumptions for high order, this is the particle to, well, actually, the particle to particle is independent of order. But these two phases of fast multipole here are assuming a fairly high order expansion. Of course, this is DGEM for dense linear algebra. So if we could migrate some of these sparse memory bandwidth limited codes to another alternative formulation, of course that would be a big win. And the secret, which has been around for 30 years now, is making, concentrating the forcing between points into expansions, which take just a few coefficients and can be hierarchically ported. So you replace this mapping of the influence of targets on sources, which will generally be the same points, which is n to n or n squared, by hierarchical clustering and multipole expansions and then re-expansions and applications locally. And in the background here, you see local P2P things for the elements which are too close to fit into the theory. We won't go into the theory here, but a picture is worth a lot of equations. This is a set of target particles representative of any place in this 2D universe. You want to have it affected through some elliptic or parabolic operator by all the other points in the universe. The ones that are close by you do directly, and the ones that are further away you hierarchically coarsen and hierarchically expand. And all these different levels are sort of data independent. You're just adding up. So it's a very asynchronous algorithm in addition to being very efficient in terms of the data that's actually transferred. So you have data pipelines of different hierarchies that are possible to program concurrently. And you have high arithmetic intensity, no all-to-all, order log p messages, order n arithmetic concurrency, tunable granularity. This is an important thing. It's like HP. You can make your expansions cover a bigger area if you're willing to go to higher order, or if you want them to be smaller area, lower. It's been inside of 8 Gordon Bell Prizes over this 15-year window. There are many effective implementations on GPUs, but the bad news is that it's fragile. The original version requires you to have the Green's function. By the way, this is just a progress in estimating the complexity, the communication complexity of the method that's part of that paper that I mentioned earlier. Here is a head-to-head comparison in the context of a real application, a 3D vortex Navier-Stokes code. This is actually a scaling example of FMM versus FFT. As you heard Kathy say yesterday, FFT requires an all-to-all transpose for at least one phase of a three-dimensional Poisson solve, and that tends to be a communication strangulation. So in this particular weak scaling, where sort of flat is good, the fast multipole already has some advantages before these microprocessor-oriented things we just talked about. You could also use it as a preconditioner if you had variable coefficients. It inverts this, but you can invert that on this, and if epsilon is smooth and small, it's spectrally equivalent. And you can even precondition a different discretization with the inverse action of the Laplacian as implemented by FMM, and in that case you should weaken your FMM because it's just a preconditioner for a different discretization anyway, and that's a way of making it cheap and more efficient. So you can use it to solve PDEs if you have a finite difference or finite element discretization of your PDE, and you want to use FMM as a preconditioner. You need to incorporate a boundary element method in order to handle boundary conditions, because FMM is an infinite domain method. But this is where all the flops go, a very effective application of this dense all-to-all matrix. This is a lower dimensional thing, also dense and small. This is like the philosophy of SPAI. It's sort of a forward preconditioner instead of a back solve. So it's got more concurrency, more intensity, less synchrony than many traditional preconditioners. This is a comparison of preconditioning a simple constant coefficient Poisson using, accelerated by conjugate gradients, a finite element discretization with FMM in its integral form for 3 different tolerances, and with traditional multi-level and Cholesky preconditioners. And of course, multigrid and FMM are sort of all good in the spectral conditioning sense. So FMM is at least an alternative that could be ready for the next architecture.
So we have to know the Green's function to the operator and to use.
So far, yes. Next point of light. And of course, each of multigrid and FMM has a different setup and per application cost, which will ultimately go into the decision of which one to sort of set from the command line if you're used to that style of polyalgorithmic solvers. Here is a comparison on Stampede going up to 1,000 cores in strong scaling, showing a slight asymptotic advantage for FMM. Much more to be done here. Both methods are good. They have their place. Maybe future architectures will give more emphasis to this alternative. Of course, if you trap FMM inside a Krylov method with all of its synchronization with every matvec, you haven't gained very much in terms of this main benefit. But there are now pipeline versions of Krylov methods. I think Jim will mention a little bit about that. They're already in PETSI. They should be more or less the defaults in machines that are stretching communication. There are many new ideas in terms of generalizing the power of FMM to more algebraically variable problems. One of them is the hierarchical matrix, goes by many other names, skeleton, HSS, and so forth. The H-squared method of Hochbusch is already about 15 years old, but mainly exists in serial libraries and in math papers. But it's ready to come out when supported by the tree-like effective implementations of FMM. And the basic idea, again, can be sketched with a picture. You have a full rank matrix. You break it up hierarchically. Here, you can't yet meaningfully replace any of these blocks with anything low rank. But by the time you go to the next level, you say, you realize, you analyze your Green's function, you realize that these points are remote and their interactions can be represented via an SVD or something else as a low rank thing. So you remove those blocks and now you say, suppose I subdivide the earlier blocks when I make them smaller. Again, we have low rank identifiable pieces and so forth, until you're left with a dense diagonal that you can't do anything about. And a union of all these blue things at different scales looks exactly like fast multipole from a sort of a superficial way, but it actually can use the same tree-based data structures. These off-diagonal blocks, which can be SVD'd, have low rank, and the basis vectors in the U and the V can actually be made part of the same basis across all the scales. Now, low rank, is that relevant? Yes. You've seen the Laplacian on, I think, every talk yesterday, so I decided to throw one in. Notice that A has full rank, but this off-diagonal block has rank 1. This off-diagonal block has rank 2. In its inverse, this off-diagonal block has rank 1. See, it's the linear Green's function decaying from the delta function in the middle of the elastic string. Even going to the diagonal, this block has rank 1. So the potential for off-diagonal exploitation of low rank is everywhere in the kind of operators that we are used to using. And here is a representation of these off-diagonal blocks as little U and V matrices here with these little Sij's in the middle. And here is more or less a picture of how you would store the data: the dense diagonals, the little dense S's, and the hierarchically processed U's and V blocks. And so the application, for instance, of a matrix vector multiply has a tree-like structure with these are the point-to-point things, and these are the sort of polar expanded things in a hierarchy. And you can imagine if this is your x vector and your y vector, you represent the x in the different scales. You carry this out with an upsweep, a coupling phase, a downsweep, and then taking care of the local points. And so this is a direction for generalizing, answering your question about the possibility. If you know enough to expect off-diagonal low rankness, then variable coefficients could be used, not just preconditioning with constant coefficients. So this is an idea, and those are its complexity estimates. Again, we're just doing a movie here. So your generation hasn't yet made its optimal algorithm contribution. 1960s FFT, 1970s multigrid, 1980s multipole, 1990s sparse grids, early millennium H matrices, but we're still waiting for you guys to add to this rich legacy of recognizing that a lot of physics operators are in effect low rank and can be scale compressed in some way. What is the potential for taking these good methods? As you heard yesterday, I think in the Cray talk, yeah, flops may be cheap, but it's still good to optimize flops, because when you're minimizing flops, you're minimizing the data that feeds them. So optimal algorithms don't become less relevant as long as you can figure out how to feed their data needs. And so this is an ongoing effort of our group. This were some guests just last May in our second Scalable Hierarchical Algorithms in Extreme Computing workshop. A little bit about Newton's method. How do we reduce frequency in, synchrony in frequency and scope? Newton's method is a notoriously global algorithm. It does a global Jacobian. It takes, global line search or trust region steps. It inverts a linear system with very synchronous Krylov methods preconditioned by level synchronous multigrid methods. We like Newton. It's good on the outside. It's also good on the inside. And maybe that's the only reasonable way to try to get rid of some of the frequency of synchronization. If you have a nonlinear vector-valued function f where you're trying to find the root, you can replace this with a nonlinearly preconditioned system. Barry Smith has a very good review paper on this that he may mention something about in his talk later, looking at nonlinear multigrid and Aspen and many other nonlinear preconditioning methods. But the basic gist of nonlinearly preconditioned Newton is that each local problem has only, all that Newton work locally, perhaps even, within a node or within a country of a grid-based, PDE solve, country by country, grid-based PDE solve or something. Each of the linear systems has only local synchronization. There's still a global synchronization every once in a while, because after all these local ones just precondition it. You want to solve the original problem. Mathematically, what you do is, if f of u is your original problem, you restrict it to a subdomain and modify the degrees of freedom that live only within that subdomain by solving Newton locally. That is an implicit definition of a bunch of t's, which could be overlapping or not. And if you add those up, that's the definition, an implicit definition of your modified function whose root you want. Clearly, when all the t's go to 0, this other function goes to 0. That's the necessary condition. The sufficient is also there if the Jacobian was non-singular at the point where you're looking. And it lends itself to a domain-decomposed SPMD implementation. It's part of PETSI, one of many options in PETSI. An example of its robustness as a solver is illustrated here. This is using full Newton on a transient application in this reservoir model, where this is the log of the permeabilities. And this is a series of time steps over 300 days of reservoir. And the per time step number of outer Newton iterations is about 3 for this preconditioned thing, instead of being much less erratic, even though using a good initial guess from here to here and so forth. Another thing that I think you'll hear more about from Professor D'Angara is directed acyclic graph-based re-implementations of dense linear algebra. So here is your Schrodinger equation. You reduce the generalized problem to a ordinary problem and do the factorizations and the bulge chasings and so forth. The 3 main loops can be arrayed in time going down and in concurrency going across like this in terms of the data dependencies of the successive operations, being very telegraphic here, because I think you'll hear more about this. But what's the point? The point is that if you look over the subroutine boundaries, you can find much higher width and overall compressed height of this curve, which is one of the directions that we want to go. And you can also, of course, if you have these dense blocks in the elimination tree, if you choose the right granularity, they're well suited for the SIMD-style thread concurrency of GPUs. And here is a project that will be reported on in SC14, where for a French adaptive octopus group, which is trying to solve dense symmetric covariance matrices in the many tens of thousands in order to guide the angles of mirrors in the European extremely large telescope in order to correct for aberrations in light coming through the atmosphere, the thing that makes stars twinkle. You can get a much better picture by sending up a guide star and measuring where the mirrors should be. So it's one of these good excuses for doing dense linear algebra along with covariance matrices and geospatial statistics. Dense linear algebra is making a huge comeback in the big data world. Even though many of the operators may be low rank, it's good to be able to shoot them in the head. And so this is an example of the application of this technology. Another student has been busy redoing dense linear algebra with tiles and with directed acyclic graphs, and actually has gotten some symmetric libraries in version 6.0 of NVIDIA's CUDA library. This is problem size. This is flops, so up is good. This compares the KAUST BLAS, as he calls them, to a variety of other things, including the QBLAS version 5. And this is the multi-GPU implementation, 1, 2, 3, 4, up to 8 GPUs, showing, some of the always, hard to model granularity effects of warps and problem sizes. But in general, a very nice reworking of linear algebra into tiles. So last little segment here is on a general philosophy for restructuring large-scale PDE and other applications. We have motivations to do this from many directions. One of the main motivations of exascale computing and even petascale is to be able to put together complex models that we might regard as individually satisfactory, like ocean, atmosphere, terrestrial gas exchange, ice cap melting, and so forth. And if you have all those codes working, the most natural thing really from a software engineering point of view is to connect them up in some time split scheme where you do the ocean and then you give some updates to the surface fluxes and for the atmosphere and so forth. So this might be a method which has a faster time scale, slower time scale, and every once in a while you get a reliable picture of the coupled system at the coarse time points. This could be, MHD, where this is the fluids and this is the magnetic field. It could be rad hydro. It could be acoustic structure interactions, but it could be ocean atmosphere. Many paradigms of this. Sometimes the coupling is across an interface. Sometimes it's in the bulk. And so we're motivated by that kind of a problem where you have independent data structures that somehow have to communicate frequently. Well, this is not just a multiphysics problem. This comes up in uncertainty quantification, where you have the state variables and the PDFs, or inverse problems, where you have the state variables and the parameters, or optimization, where you have the state variables and the designs, or visualization, where you have the state variables and their rendered variables. And so we often have several sets of variables that more or less cohabitate, but we created them in different codes, and the question is how to link them up in future hardware. Today, separately, black box algorithms may not live well if you don't pay attention to the locality of the things that tightly couple to one another. And this is a nice graphic from Bill Gropp to illustrate that if you had a 3-component climate model, you wouldn't put the ocean on this set of processors and the ice on that and the atmosphere there. You would try to cluster together things that were near each other. And if you had performance reliable processors and good adaptive load balancing to follow the different physics as the Earth spins and sometimes the atmosphere is photochemically active and sometimes not and so forth, then you could partition like this. But if you don't even have hardware performance reliable, then you're going to be constantly doing load balancing within a NUMA-constrained atmosphere and probably end up doing something like this. And a couple of years ago, DOE brought together we the people in order to assess a whole bunch of different multi-physics opportunities. Many people in the room contributed to this particular write-up. How will PDE computations like these and their post-forward models adapt? Well, the programming model will still in the near term be dominantly message passing because we have a large legacy code base. Load balance blocks will still be scheduled with nested loop structures, but we will separate them into the critical parts for that kind of scheduling and the non-critical parts to fill in the gaps for the less reliable performance. And the critical parts can be DAG scheduled to increase concurrency and reduce synchrony within preserving that critical path. And you heard several examples of either languages or libraries or runtimes that will help accomplish this for you at different levels of user involvement. And the non-critical parts will be made available for stealing within, of course, the constraints of not wanting to move things too far in memory, maybe stealing within shared memory. But in order to take advantage of this kind of a model, we need to rewrite our codes because right now we keep everything in one loop. For instance, in a Newton method, we linearize the Jacobian, we factor the Jacobian, we stick it in as a preconditioner. We do all those things that really aren't on the critical path because we could use the old Jacobian or the old factorization. but we do them at the same frequency and schedule that we actually compute the Newton step and do its line search bound and so forth. So what we need to do is get more in the style of programming like an operating system that handles tasks of different priorities and schedule the priority ones in a critical path and let the non-critical ones fill in. So this is the critical path of a Newton solver, a linear solve with a Jacobian bounding the step and updating the states. And these are all the things that could conceivably pad a non-performance reliable distribution of work. Either locally by sharing work or even by skipping some of these steps with small local damage to the convergence rate. There are many sources of non-uniformity that will interfere with carrying BSP methods to a billion cores. Some of them are already important. Mark Adams has a famous description from Berkeley how one processor with a TLB cache problem made the other 999 slow down in a Newton Krylov code. But there are new important ones that come from dynamic power management, correcting soft errors, and the software-mediated resiliency that we've been talking about. And then algorithmically, we've always had these non-uniformities. And at a synchronization point, who cares where the non-uniformity comes from? It looks the same. It's a problem that has to be solved. And so as we conquer these in preparation for exascale, we actually relieve programmers at the petascale of some of this non-uniformity of load balancing. Well, Jim asked me about randomized algorithms. I didn't take that on as a point of light. I just have it as a bullet here. This was a very nice talk from Jim at that meeting on what was it called? Parsimonious. Parsimonious, yes. Right, yeah, right, for precision. And I was actually incredibly blessed by going to this meeting and seeing these 74 two-pagers are still online at this DUE address. And again, I'm assigning PhD theses. There are a lot more beside these. I think Pete Beckman started off the workshop with this slide in terms of things that are trending down. Coming from the architectural point of view, less dependence on checkpoint restart, more on algorithmic fault tolerance, premium on data instead of premium on flops, and so forth. I would like to add some things from an algorithmic point of view. Trending down, system-controlled data replication, system-controlled error handling, default high precision, computing directly with the quantities of interest all the time, low-order discretizations, which are not very arithmetically intensive, default full rank in the operators. These are the directions that we should take the numerics. And a basic algorithmic theme is we have to defeat the curse of dimensionality and the curse of multiple scales. But we have the blessing of continuity and the blessing of low rank. And those are the only tools that we can really bring into this fray. The SIDAC philosophy, which I hope you're all getting deeply imbibed in and will later today through the FastMath project, is basically that many applications share the same process needs: dense linear algebra, eigenproblems, sparse linear algebra, integral equations, particle methods. And a handful of really good projects and really good implementations by people like the ones that will follow me can then serve a wide variety of these applications. And these are examples of some of the projects at KAUST at the moment. So with that, I guess I have several minutes for questions, and I could revisit slides that I went over too fast. I was more worried that I wouldn't be able to get through all my examples, but thank you very much. Yeah.
So for your new paper on the fast multipole, can you say anything about what new ideas you had to reduce the communication?
Let's see. The question is, where do the communication reductions come in fast multipole? I think it's a lot like your philosophy. They were there all along. You just had to, improve your understanding of the algorithm to find them. These represent different. Let's see. This is the number of processes for different models coming from the literature. And this is the work primarily of Rio Yokota at KAUST and Huda Ibed, who's a PhD student there at the moment. Basically, just exploiting the tree-based structure of the code and the opportunity to do more things synchronously, asynchronously than in the original, GreenGuard specified version of the algorithm. The actual local communication in terms of, this is for a 3D problem, by the way. The generalization here is d minus 1 over d for the local data. And the logarithmic complexity of the global communication is essentially coming from the hierarchical subdivision of the domain into quad-tree, octree, whatever. I actually, I'm not. I don't know the tools that were being employed in the earlier days. But this is a fairly physically. This is what you might expect from a lower bound. If you can, typically following the implementation is a good way to,
So it still uses locally essential trees and sort of replicating things?
Yes, that's correct. Sir.
Are there any available, like the fast logical method library? Yes,
there are actually many open source fast multipole libraries. One that you might want to look at is EXA-FMM, EXA-FMM. That's the one that Ryo Yokota has available. But I think there are about half a dozen now. They vary in what they're, for instance, this HP. Some of them are H-oriented. They make the subdomain smaller and keep the order of the expansions constant. Others keep keep P constant and vary the subdivision. Ryo's is one that allows both to vary, which is useful in the GPU world because you might want to fix the order to map onto a warp of a fixed size and just vary the number of blocks, similar to Marcia Berger's original implementation of AMR on the connection machine, where she wanted a fixed granularity of work and didn't care how fine you had to make the mesh in order to get down to a block that size. So that's a good feature of a method, to have that HP variation. Some are implemented well in MPI. Some have, the OpenMP, CUDA-like extensions. There's, I think, a comparison paper that was put together after our 2012 Shaxi workshop that solved a few model problems with constant coefficients and compared some of these methods.
I'm just curious if you show again the the current trends, the slide where you have the trending up and the trending up.
Yeah.
All these approaches can work concurrently, or some of them might exclude?
That's a good question.
In particular, I'm just looking because you mentioned adaptive variable precision, but then, for example, if you use hardware discretizations and now you reduce the precision, then how are you going to get that?
Right. So one of the greatest challenges here is the precision one, because it requires a lot of co-design. The hardened, the constant precisions that we're working with have enormous efficiencies in terms of memory layouts and things. So the question of whether the good algorithms can be implemented on the good architectures is one that actually drove a workshop that Lois just chaired in Breckenridge earlier this week about updating the Moore's law for algorithms and the Moore's law for architectures slide. We've always assumed that we can take the product of those two advances, that chips are getting faster and algorithms are getting, more flop and byte efficient. But that's the whole crux of co-design, right? That assumed multiplication of improvements may not work in the future. We may have to look over the thresholds and get more synergies there. So Jim, I don't know, I'm not sure if parsimonious is part of your talk, but it always seems to me that it's easy to see when you can degrade your precision, but not easy to see when you need to crank it back up.
So I wasn't going to talk about it.
I didn't think so.
It's a tool that attempts to, given a set of model problems, and let's say one implementation that works all in high precision, it gives you an answer that you trust. And then, but if you run it all in single, say, then you get garbage. And the question is, what are the fewest number of variables that have to be run in double precision in order to get an answer within some threshold of all double? And it tries to do that by a kind of a binary search technique on variables in the program using ideas that were adopted from the programming language community. And yeah, so that's an ongoing project.
Fortunately, Jim is mic'd, so I don't think I need to repeat that answer. Our AV guys were quick to switch that over. You know, the classic example is iterative correction in linear algebra, where you compute, you know, you do the n-cubed work in single precision, you reevaluate a residual, and based on that residual, you compute a correction. And there are many, we haven't looked there for a long time because we just by default enjoyed yeah, and it takes away the numerical analysis, right? So, but now, you know, it's an invitation because of the leading order cost in energy and time to get back to that. So, as Jim suggested, you can do it by, you know, finding with some kind of a binary search technique where you want to operate most of the time, and then maybe harden that for your production runs. You know, but it's hard to know how to do it completely adaptively.